Okay, then we want to do it by hand. Well, the correlation coefficient is just given by these numbers and by these formulas. And these formula, if we look at it, how do we the normalization? How do we the normalization? And for this, we just have a look at this part of the formula. If we look at this part of the formula, then we can say that this is, of course, sum xi minus y bar over 1 n minus 1 times yi minus y bar over, and we take in the root 1 over n minus 1 sum over xi minus y bar squared times 1 over n minus 1 yi minus y bar and the sum squared. And from this then we see that this is nothing else than the covariance and the variance, the covariance of x and y and the variance of x and y multiplied by each other and taking the square root. And what does this mean? This also means, when we take the last week, our lecture, that we also can interpret our correlation coefficient R as the slope of our linear line times the proportion between the variances of both variables and taking the root. So what we are doing, we more or less normalize the covariance via the product of both standard deviations. So in general, the covariance is normalized by the product of the standard deviations of x and y. And of course, if we look again here in the definition of the covariance, and knowing that covariance of xx is variance of x and covariance of yy is variance of y, then we know that the denominator has always be in absolute value larger than the covariance, and if x is y, then of course we obtain in this case here our number 1, and therefore we obtain that R is element of -1 and 1. And here, of course, we have to take plus minus in front of these intervals. Because then, so in general, but this is of course only a rule of thumb, because interpreting then your correlation coefficient, you also have to go in your setup, because sometimes you even only expect only an R of 0.3 or something like this, and then you are already very happy to show at least some dependence. So this is here only something like a rule of thumb. If you say that if your R is in between 0 and 0.2, then you say, well, we have almost no dependence, low dependence from 0.2 to 0.4, medium dependence 0.4 to 0.6, and high dependence 0.6 to 0.8, and that you say you have almost a full dependence with 0.8 up to 1. Okay, then if you look more or less at these data points, what do you think? In which area will you find the R? If we take here the first one, what would you think is roughly your R in this case? Just make a guess. So what do you think? Do we have a quite high dependence between X and Y? So here, of course, X and Y is missing. Do you think in the first case we have maybe a dependence shown by our correlation coefficient of 0.1? Just make a guess. What do you think? You still hear me? Well, then let's go at first to this diagram at 4. What do you think is R here? Actually, looking at this data, and if I tell you that these data points are distributed totally symmetrically, then we even can say what is R in this case. So you just have to think about R and fitting at that point just by eye a line through the data point, the data sets, and if you fit this line, then you can say, well, is the spread of my data points very far away from my data line or not? And if the data points are quite far away from your fitted line, then your R should be in absolute value quite low. And if they quite narrow around your fitted data line, then you should be in an area around plus or minus 1. So here 0.2, this is, yeah, a quite good guess. So you should you think about a quite low number. This is okay because here, how should I put my line in here? In this way, in this way. If I said you that this cloud of data points is totally symmetrically distributed. And then, and here we have the right answer. Here we really can say that R is 0, since there we have no idea how to fit our line because of the symmetric data points. This line here is as good as this line here. And therefore, in this case, we have R is 0. Then let's go to the third diagram. What do you think is here? R, if you look at it just by eye, then I think you can make an assumption what kind of data points I've used in this diagram. 0.8, this is again quite good. And here I also tell you that these data points are just created by a deterministic function y is a plus b x. So in this case, yeah, of course, you can only guess if this is true, but I say it to you that in this case, really all data points, and I think I can show it you here, taking a line. Oh, missed. Up again, taking just a line. Uh, Then we see here all data points are on the line, and this means R is 1. And I think we take your 0.8 then for the first one, because within here, let's take just this line here. If we maybe fit something like this here, then you see also just by eye, we can find a linear line, which is where the scattering is quite narrow around this line. So let's think that this is 0.8. And then let's take your 0.2, which is also maybe a good guess for this diagram here. But should we take 0.2 or should we take another number? What do you think here? Maybe our best fit looks like this. Then we see, okay, the scattering around our line, the points are quite far away from it in some, but so we are somewhere in the neighborhood of 0, but should we take 0.2 or another number? What we have learned. We have information not only from the magnitude of R, but also from the dependence if we assume that y is increasing when x is increasing or y is decreasing when x is increasing. And in this case, we have y is more or less decreasing if x is increasing. And what does this? So it's lower than 0. Yes, of course. You should take here a minus, and therefore let's just assume that here we have roughly minus 0.2. Great. So, and then R should be negative. So, and now hopefully I find the right file for the true values. Oops. Linear regression. And the other file is this one, hopefully. Yes, here we are. So this is the data I took. Do you see it already? Almost. Then I have to move it a little bit. So here, this is number 1. And I think here I had my R values, or no? Where are my R values? Here they are. So for the first one, we have 0.985. So here, true value R is 0.985. In the second case, we had a bit more, 0.465. R is 0.4 minus 0.465, and within here are the other ones. Oh, there, of course. We had R is 1 and R is 0. So also with your guess, you're maybe somewhere in the neighborhood of the true values which I created from specific data. Okay. Then some properties from the coefficient of determination, because quite often in statistics we are not interested in R, but we are interested just in r squared. But be careful, if we take r squared, the coefficient of determination, then the information from plus minus in front of from the sign of our number is vanishing. But maybe you can keep in mind, well, looking at the data, I already have seen that my linear line is decreasing or is increasing. And why do we? So we have not this plus minus anymore, but why do we this? And the reason for this is that this r squared has a quite nice graphical interpretation. So with r, we only can say, well, it's high, it's low. But if we take r squared, then we can say that the number of r squared, and if r is in between -1 and +1, then of course r squared has to be within the interval 0 to 1, since r is element of -1 and 1. That we can interpret this number if we have there, for example, 0.7. Then we can say that this number 0.7 means that our linear line is explaining 70% of the dependence between the two variables y and x. And this is then quite nice, because then we can say, well, we already have explained 70%, so I have to look only for other reasons of determination for the dependence between x and y, which is only 30% left. And then, of course, 1 minus r is this left percentage where we have no explanation out of our model. And here, this graphical interpretation again. So, in general, we have here our fitted line. The dotted line here, this should be the mean. So this is x bar. And then, of course, if we take this data point here, then we can say that the distance of this data point with respect to the mean, this is, which we have learned in our introductory courses, this the squared distance of the squared distance from my data point with respect to the mean. This is measuring, something like how far is it away from it. When I take the sum of all these squares, then I come to the variance, and then of course, the higher the variance in my data set, the higher is the volatility or the spread in my data set. So, but this is a horizontal line. And now we want to do a better fit than the horizontal line, because quite often we take some data set, we ask 1,000 people here in Wilhelmshaven, how do you like the weather here? And then we say, on average, they told us when they have to choose a number between, let's say, 0 and 10. On average, the people in Wilhelmshaven tell us they give the weather here 3.5 points. But then we know that many people are away from this average. And in order to increase our explanation, we go to this linear line as a fit. And then, of course, we can say that this part here is the explained difference. There we moved up. And the left part up here, this is then the not explained distance of our data point. And of course, we discussed that we don't take the distance, but we take the squared distance. And then we can say that this here is the total squared distance with respect to the mean. This is the explained squared distance, and this is the not explained distance. And so we can divide the total sum of the squared distances into the sum of the not explained and the sum of the explained squared distances. And then we can show, and this we will do, I think, within an exercise, that our coefficient of correlation, our squared coefficient of correlation can just also be written as the sum of the squared distances divided by the sum of the squared total distances. And so to speak, we have a percentage how much is our modeling A plus BX explaining for our data set. So after all this theoretical introduction, of course, we want to do this in an example, and we take, of course, our example which we have already used for our linear regression. So in order to do this, we just go again into our data sheet. And having our data sheet, a bit to the right, there we of course need at first the theoretical values of y, so our y hat here. This y hat is in our picture here always just the points which are lying on our line. So we had in our example A and B. Where do we have it here? 1.98 and 3.92. So here our fitted line was y hat is again 3.92 plus 1.98 x. And with this, we just calculate our theoretical values. For x is 9, we had a data point y is 24. So we obtain the corresponding theoretical value with a plus, and we should keep this, so a double dollar. Why is it not working? Not snow. Plus B. Oh, missed. Again is A plus B times 9. For this, we obtain 21.72. So let's write it here. This would mean then 21.72, and this is then given by 3.92 plus 1.98 times 9. And having this number, we just can move this one down, and we obtain 21, 25, 13, and so on. In order to calculate our R, we also need the explained squared distance. So this is the, oh, this is by hot bar, yeah? This is explained. So here we obtain, opening the bracket, then y hat minus y squared 5.18. So in this case, this is 5.18. So this is y hat 1.72 minus 24 squared, and we need the total distance, and here we take, opening the bracket, 24 minus the mean, and the mean was here, down here, 27. Oh, sorry, the first one is wrong. I just see. Oops. And this, we need two dollar signs. But here, sorry, this is y hat minus y bar, so we need here our 7, because y bar is 27, and then this is not 5.19, but we have C12, 27.83, and all this we also take down here. And so these are the singled explained distance, squared distances, and the single total squared distances. And what did we also wanted to do is to calculate our correlation or coefficient of determination, and this was given by, oops, yep, the sum of all explained squared distances divided by the sum of all total squared distances. So what we need is the sum here equals not this, but equals sum of all these numbers and these numbers here. And so we obtain r squared equals 487 over 572. And how do we obtain then r? What do I have to do? Yes, of course. So taking the square root, we obtain 0.92 roughly. And what else do we have to do? Not only taking the root, but also we have to look at the data, and let's just show how the data looks like. So, because what do we also have to keep in mind when we are at first calculate the coefficient of determination, and via this we calculating our coefficient of correlation. Since we have two numbers which are, if we square these numbers, we obtain 0.4. What could be also our result? Not only 0.1, 0.91, our coefficient of correlation could also, if we don't look at our data, this could be, of course, also negative, but then if we look at our data, then we see here that we, of course, have a positive dependence, and if we have a positive dependence, then we, of course, need the plus sign here. Okay, then I will also put this all this in here. Oh, this not this this can up. So let's take this one and this in here, and as a result 0.4 and 9.2. 0.92 and no, the other way around, 0.84 of course. So r squared is 4872 over 572, and let's take also this picture here. So we have a positive dependence and therefore taking the root for calculating R, we need the plus sign. So, in order to sum up, we can say that our coefficient of correlation or our coefficient of determination, this measures the strengths between two variables x and y. R squared can be interpreted as a proportion explained by the linear regression, and of course if R squared is 0, then B has to be 0, and we are not better than taking just the average of our data points. And then we can say more or less say that x has more or less no influence on our dependent variable y, and in opposite, if R squared is 1 or is very well in the neighborhood of 1, then we are quite close that, oh, we have here y, I, and below. Let's see if this works here. Einfügen. Because this we can also use in PowerPoint. Maybe you have already seen this and you know this. That in this case, yeah, where are we? Symbols, formula, where is it? Then let's go here and symbols. Why is this not changing? My menu. So again, there it is. This I wanted because here you can also take just writing your math. So let's take maybe sum of y equals 1 up to n y I, and this I wanted to have. Let's take this, and here I have my y I. Oops. There it is. Here we are. So that in this case, we really can say that our, back here, reduce it. Our theoretical value just coincides with our measured data point. Okay, and in the end today, of course, we have really calculated many things by hand. Quite often in other courses, you are really asked to do all this via your calculator. Then you can think that you are sitting here about 20-25 minutes in order to obtain this table. But of course, within some software package, this can be done much faster, and this I also want to show you. Because here, remember, B was the slope. Oh, you don't see it? Here. Remember, B was the slope of our fitted data line. And this slope we of course can also obtain taking what is German for slope. In in the English version, I think you will take there the name will be slope or something like this. In German it is Steigung, and then our y numbers and the x numbers, closing the bracket, and hopefully I'm in business and you see these numbers coincide, and also here. And the German word for the vertical axis point is Achsenabschnitt, y and x, enter, and we are also in business. So then we want to calculate our coefficient, our determination coefficient. This is called in German Bestimmtheitsmaß. And again, the y values and x values, and we are done. I'm happy that we have calculated in the right way, so we obtain the same numbers. And here I think it's coral. No, it's coral axis. Oh shit. So hopefully it comes back, because otherwise I don't know if you see what I see here on my table. Yes, it comes back. Now coral is it not? How was it? So I have to look it up, but otherwise you just take the root and you are also done. And the last thing is, and this is quite nice, within the software package here, you just click on your data points, right click mouse. Oh, let's go a bit higher here, then you see it. Click on your data points, right click mouse, and then you have in the menu Trendlinie hinzufügen, so doing the linear regression. Then you see here, this is on the right, so I have to move this here, then you see it. Then you have a menu. Do I want to do my regression exponentially, linearly, logarithmically, with a polynomial, or some general potence? So we take linear, and then we can choose here. Please show me the formula, and please show me the coefficient of determination. And here we are. And so we can, of course, directly calculate all these numbers using your software package. But on the other side, again, I really want that you know what you're doing. And I think in order to know what is meant by the coefficient of determination, you maybe should take this diagram, this picture. You should keep this in mind, and then you are really knowing what you are doing. And this is, yeah, the most important things. Not only always looking on your data, but also knowing what to do with your data. The next week, I think we will make some practical example. And this, I thought this morning, we could take, and I will paste it also in Moodle, that we want to fit or make a forecast for inflation. And this we will do first. Take the oil price of what we will be doing. Let's take the last 5 years. And take monthly data. Then if we take the oil price, today the oil price is roughly 100 US dollar per barrel. And if we want to make inflation forecast for Germany, what do we have to do then? Can we just take the oil price in US dollar? Or what is relevant for us? Hmm? Are we paying in US dollar? What is the currency we have? In euros, of course. And therefore, relevant for us is not the price in US dollar. Relevant for us in Europe, in the EU, is the price in euros. So we have to take the exchange rate. And then we make a guess about the dependence of a part of the HCIP, the Harmonic Consumer Price Index. This has an energy component, and this energy component is correlated, of course, with still the most important energy good in the world, and this is still oil. So calculate the dependence between the energy component of the HCPI and the oil price. And in the end, then this is a very strong assumption. We assume that all other prices without the oil price, without the energy component, should be still the same. And from this, we just then want to calculate the inflation, which is just coming from our dependence between oil and energy component due to the higher oil price we have right now, and maybe it is increasing when we start the embargo against Russia the next week. So and then calculate the inflation, the total inflation coming from the increase or the guessed increase of oil prices in the future due to a possible embargo of Russian oil. And this we will do next week. And maybe you can start. Because, of course, for this, you have to find the distinct oil price. You have to find the data for the exchange rate. You have to find the data for the energy component of the HCPI. And then, of course, we will do the regression between energy component of HCPI and oil price. So what we want to do is energy component and oil price in history. There we have hopefully some positive correlation, but I can promise this will be a positive correlation. Then we want to fit this data, and then if we assume that in the next month we will have an oil price maybe of 150 US dollar, we want to forecast this point and then taking this point for total inflation. Okay, so we are done today, and I'm stopping the recording.